Which question did you do? I
No?
only counted 4 to 3.
But see me after
Okay.
if you have questions.
All right.
Let's just get started with the class. So we left off we started with proofs involving real numbers, and I think I proved a couple lemmas that I want to use to prove the triangle inequality. Before that, so on the last one, also, something that stood out to me. I believe this was homework 3, problem 28. It said something like, if x, y is odd, x and y are odd, or something like that. Right? Of course, x, y are integers, blah, blah, blah. Most people did this wrong, so I just want to make sure that there are no, like, what the misunderstanding is. How would you actually approach it slowly? Because most people seem to jump into all the cases about even and odd for x and y, and then they make a conclusion about x, y. Yeah?
I did what you just said, and I tried to do the contrapositive using all the cases of x and y, or rather x or y are even.
Right, but I mean, people did all the cases, including both are odd. So yeah, if you want to do the contrapositive, which is probably what I would do because thinking of a product as being odd is going to get you in trouble. If you want to do the contrapositive, what would you assume?
X and y are even, or I did the without loss of generality, I did one even, one odd as
Well, tell me the basic statement first. What would you assume?
X or Y are even.
X or y are even. Right? Now, what are the cases inside of it?
X are even or Y are even.
X even
Y even.
and y even, so that's if both are even. We could have x even, y odd, or we can have x odd,
Y even.
y even. And that's it. Right? A lot of people jumped into the 4 cases of all the possible combinations of x, y, even, or odd. No, if you're doing the contrapositive, there are only 3 cases to consider. So there are some people who assumed x and y were odd, and they showed, okay, so if this is odd and that is odd, I can write this 2k plus 1 and that is 2l plus 1, and you multiply them, we get an odd number. What do you actually prove if you say that? You are proving the converse, you're not proving the statement. If you start here and get there, you're not proving the implication in this way. That's something you should recognize that you're not doing. So the moment you start x odd, y odd is one of your assumptions, you're confused. You're going in backwards. This is not a starting point. Okay? If you start here and end up with x, y is odd, you're going that way. Okay? You want to go this way. Now obviously starting here is going to be sort of tricky, so you want to start here and go that way, but in order to do that you have to use the contrapositive, and the contrapositive means you have to assume not this. And if both are not odd, it means one or the other or both are even. It does not mean that. So the moment you start writing this, you're going backwards and you got confused about what you're supposed to be doing.
Question. Could you do like all those cases, then see which cases don't meet the initial condition?
No, because that's not, according to our truth table, that's not proving
No.
that's true.
So say that like you do a direct proof of that, right? And then like on the side you see like all the combinations and say like you say x is even, x is odd, y is even, and then the other case, but then those 2 cases won't fit that, so you just like leave those away and say that okay, the only way this is possible is with the other cases. That's possible, right? Or-
Isn't that saying if x and y is odd, x and y are, if x, y is odd, x and y are odd, because if x, y is odd, x and y are odd?
No, I'm saying like,
What?
No,
Oh, I
at least
didn't
that's
hear
how I
that.
interpreted that, like starting from if x, y is odd,
Yeah.
then x and y are odd, because if
That's
x,
what
y
you
is
need to
odd,
prove, right.
they must, yeah.
no, what I'm showing, no, what
Right,
I'm,
but it is a P implies Q is the point. And how do we prove that? Right, there has to be a starting assumption. Either you're going to do it directly and assume P, which may devolve into a bunch of cases, it may or may not. Or you can do it indirectly and assume not Q. Of course, there are other techniques, but that's not the technique that you guys did. What you guys actually did, if you were to take all possible cases and say, oh, well, this will only happen if both are odd, you're actually proving this.
well, I mean, but that'll suffice too, right? Because it's stronger, if that is true.
Sure, if you knew that's what you were doing, and you can say, since I proved this, obviously one direction works. If you had a sentence explaining that, sure. But to me, it seemed clear that what people did was they did all these cases, and they're like, oh, none of those work. And then they did this, and they said, oh, that works, therefore I can conclude this. That seems to be the argument that I saw being made. And that's an argument for the converse, not the statement.
I don't remember what I did, so I should.
But a lot of people did similar to that. They put all four cases, and they're like, well, none of these work, it has to be that. You're proving the converse if you say that. The moment you throw these away, you're proving the converse. If you take all of them together, you're proving the bi-implication, and then you can say, if the bi-implication holds, then either direction holds. But you have to have that statement there. But no one created that argument correctly.
No, so it's like, oh man, I mean, actually, like, it's not really, it's like, all possible cases, right? And so the proof starts with assume that that's true, x, y is odd. And then I'm doing like a little detour with the pairs, right? And then I'm asking, okay, for that to be true, and I have the all cases, then I can deduce that some of the cases are not what I'm looking at. And I won't be looking at those cases. And I don't know if like,
Exactly, but listen to what you just said. You said, for that to be true, these cases have to work.
yeah, but
Exactly. So that's
I
what I'm
can
saying.
use
So
that.
if you said P implies Q, another way of saying that is for Q to be true, P must be true.
no, I'm saying like, for the P to hold,
Yes.
I'm saying that, and then I'm seeing all, so the four possible combinations.
It sounds to me making.
Yeah, but you're not supposed to be proving P holds. That's not the point. You're supposed to be proving that Q holds under the condition P. You're not supposed to be proving that P holds.
If you're starting with the assumption that P is true, you don't need to prove that P is true.
No, that's not what I'm saying though. I'm saying like,
Yeah, you can't start here and it doesn't
I'll
work.
write it out.
It doesn't work with the techniques, at least with the techniques that I've shown you so far. Like no one who did all the cases constructed the argument properly. Yeah, but that one kind of jumped out at me. For the most part, most people were actually doing okay. I mean, problem 12 seems to have very suspiciously familiar wording on several people's papers, but whatever. As long as you know what you wrote down and you understand why it's correct and how to express it. But if you're doing it direct or indirect, which is all we've covered so far, you can't construct the argument that way. You're either going to assume this, which is problematic, or you're going to assume that. And if you assume this, and then you go over and deal with all the cases of Q, and then come back to that, you're proving this way regardless, which you're not supposed to be proving. Anyway, let's actually continue. So we are in chapter 4. We are doing proofs involving real numbers, and there are many. We're only doing a few examples here. There are many things that we can talk about here. Oh, something else I wanted to mention. So That was an error I saw in the homework, but I wanted to correct an error that I actually made last time in my haste. Because we're going to be covering congruences again in chapter 8, so I was just kind of rushing through it at this point because we're going to be looking at that deeply again. But there was a question about division or cancellation on both sides. So under what conditions, if we have Ka is equivalent to Kb mod n, can we say that we can essentially cancel the K on both sides and say this? Right? When is it okay to say that? Was a consideration. Now there are a couple of considerations here. One, I mentioned it has to be non-zero, but what I should have said is it must not either be congruent to zero either. Right? So that's going to be important. Division is very weird with these things. In general, it's not defined for congruences. It's defined some of the times, and we'll get into some of the. Basically, you can only divide both sides and cancel at will if this guy's a prime number, and we'll talk about why that is when we get to chapter 8. Right? Otherwise, it's kind of iffy. Sometimes it might work out, sometimes it won't, and there are special conditions under which it will work out. So there's a division operation isn't really defined for congruences. There are times when you're able to actually do this, though, and there's a general theorem that has a corollary that can tell you when that can happen. And again, I don't want to go too much into this because it's going to use something that we haven't spoken about yet in detail, so I'm just going to say it. You guys know what it is, but we haven't dealt with it rigorously yet. And so basically the claim is the following. If you let D equals the GCD of K and N, okay, this is the greatest common divisor. Some people call it greatest common factor. It's the same greatest common factor that you had from algebra class. When you want to combine fractions, you find the least common, right? That same kind of guy. If you let that is true, then it turns out that K is equivalent to B mod N, if and only if. If you divide both sides, you have to mod it by that. And it turns out, therefore, as a corollary, if we have that the GCD of K and N is 1, meaning they have no common factors. They have no factors in common other than the number 1. Another way of saying is that they're relatively prime. Then that means you can just plug in a 1 here and the mod won't change when you divide both sides. And you can divide and multiply both sides at will. Right? The multiplication definitely works, but the division or cancellation is kind of weird. There's a GCD factor here. And I can show you one of the reasons why it's very strange like that. Let's say we're doing mod, what do we have, mod 4, whatever. Okay. Can you tell me some things that are equivalent to 0 mod 4?
Multiples of 4.
All multiples of 4, right? So if I put 4 here, that's true. If I put 8 here, that's true. Put 16, any multiple of 4 would work, right? And it's also going to be true if I put any multiple of 4 on either side, right? So I could have, say, a 4 here and an 8 here, and that would be true, right? Because they both have remainder 0 when you divide by 4. So they're both equivalent on 4. So the idea is your 4, while it's not 0, it's equivalent to 0 when we're talking about this equation. Right? Meaning, dividing by either the 4 or the 8 is somehow tantamount to dividing by 0. So it turns out that if you were to do something like divide both sides by 4 at this point, what would you end up getting?
Oh, it's not the one.
Right, you'd have 1 is equivalent to 2 mod 4, which is obviously not correct, right? And the reason is, you're multiplying something on both sides that is a multiple of the modular, of the mod that you're using. And that can kind of mess things up. It's kind of like when you have an equation, you multiply both sides by 0. Even if it wasn't equal, even if both sides weren't equal to begin with, multiplying both sides by 0, you lose all information as far as you're concerned. So there's kind of a little sketchiness with the division. And it turns out you can only kind of do something like this when your mod is actually a prime number. And in that case, it's going to work out differently. So I just want to mention that. We'll definitely come back to this, and we'll talk about the integers mod n, which is the equivalence class that we get from these guys, which we mentioned last time, but we're going to define them specifically in chapter 8. I'm not sure if I'll delve too much more into this stuff, but we might. So that's just, I just wanted to make sure to clarify that. So these are the conditions under which you can divide both sides. And if you want to maintain the mod that you're using, you have to make sure that the constant you're dividing by has no common factors, no factors in common with the n that you're using. Just wanted to mention that. Okay, now let's move on. We proved 2 lemmas last time. What was the first one? It was x, y are positive real numbers. Then if x is less than y, if and only if x squared is less than y squared, right? Was that the first one I proved?
No, you did for all x in real numbers, x is less than or equal to the absolute value of x.
Okay, so this was the second one I proved. Okay, so the first one I proved, lemma 1, was for all x in R, x is less than its absolute value.
Less than equal to.
Okay, good. Okay, so those are the 2 things you proved. Now what I want to do is to use that to prove the triangle inequality. Now your textbook has a proof of the triangle inequality, but I want to give you a different proof. Something called the triangle inequality. It's a very important idea. We use it all over the place. So it basically says, and it generalizes beyond the real numbers, but for now we're going to talk about just in the real numbers. If x and y are real numbers, then if you take the absolute value of their sum, it will be less than or equal to the absolute value of each part's individual. And your book proved this by going through all the cases of the absolute value, where it says, oh, pretend this is positive and that's positive, and then this is the same. Pretend this is negative, but that's positive. Pretend this is negative, and that's positive. Pretend both are negative. And they basically did a proof by case, and they worked through all the cases, and they found this to be true. Okay? But I want to do actually a different proof, which is more computational, and it's going to be shorter, but I just want to expose you to some of the things that we can do through numbers. So we ultimately want to prove this. And we're going to use both these lemmas to prove it. Do you guys remember the definition of the absolute value?
After x is equal to.
But that's something you have to remember. Right? So at any given time, I can use this on a test, and you should know what it means. So piecewise function
Is equal to x if x is greater than 0.
Okay, so that's something you should also always keep in mind. You can actually prove that this is equivalent to saying the absolute value of x is the square root of x squared. That's something you can prove. But the goal here for now is to prove this guy. So here's what we're going to do. We're going to start out with squaring this absolute value. I don't know if any of you have seen this proof before. Now that turns out that it's the same as just squaring the regular value. Is that okay to say that? Is everyone's okay with that? Well, they're both positive, and you can think of, if the inside is positive, then it's going to make no difference. If the inside is negative, then it takes on this form. You put a negative inside the square, and the square kills the negative anyway. Right? So it's all going to be the same. Okay? So it turns out for squaring an absolute value, or raising it to any even power, it's the same as just raising the regular thing to even power. So what we're going to do now is we're just going to expand this guy. To xy plus y squared. By the same logic, these squares I can replace with their absolute values again. Now what can we say? Does anyone see the next step? What can we actually say? Does anyone see where I want to end up? Do you realize where I want to end up?
The right hand side is bigger than the left hand side.
Sure. I eventually want to get that this is less than or equal to something. What is that something?
Absolute value of x squared plus absolute value of y squared. Somehow.
Absolute value of x?
Squared.
Oh, I see it. You can take the individual absolute values.
Well, no, that's not what I want to show, because that wouldn't really...
No, like, what I'm saying is that thing will be less than or equal to, you know the middle term?
Yeah?
It's the middle term. So, plus 2, absolute value of x, absolute value of y, plus, and that holds because...
Right, why?
It's the definition of absolute value for any given...
That's not the definition.
I mean, you're applying that for like the inner term.
Oh, by
So you have
Huh?
sorry, by one.
This guy.
One or
By level
two
1.
or
oh, yeah, sorry.
Right? The absolute value is going to be bigger than this guy. So if I replace this with absolute values, I end up with something that's bigger than the original. And what is this guy?
How do you call that? Yeah, that.
It's just the sum of the squares of the individual absolute values. I.e., what we've proven is that absolute value of x plus y squared is less than or equal to absolute value of x plus absolute value of y squared. Now what?
Take the square root.
We can take the square root, or we can actually apply something. We can now apply this level, right? Tells us whenever we have positive things, then if the squares, the relationship between the squares must be the relationship between the two numbers, right? This also includes 5.0. So this is going to be x plus y is less than or equal to x plus y. So it's just another version of the proof by triangle inequality. There are many proofs for triangle inequality. It's a very important thing. People have proved it in multiple ways. But I decided to show you some tricks that gives you some more, a few more weapons in your arsenal for the real numbers. So you can know, you can use these facts at any given time. And of course you can use the triangle inequality at any given time. There's also something called the reverse triangle inequality. Now this one includes the subtraction of absolute values. And it says that that inequality holds. proof you can do pretty similarly. If you start with x minus y squared, this is x minus y squared is 2xy plus y squared, and replace this guy. Now what happens is, now when I replace these guys with their absolute values, I get something smaller because I'm now subtracting something bigger. And so it turns that way. So x minus y is greater than or equal to x minus y by 2. We can get a corollary for this, which also shows up all the time. Like when you do a course like advanced calculus or studying metric spaces, things like this will pop up everywhere. And more generalizations of this, like the Cauchy-Schwarz inequality and all that sort of things. So it's nice to just see them. We can do a corollary here, which is to say that x minus y is greater than or equal to x minus y without the absolute x. I might show you a cool application of this, depending on how far you get. Maybe if we start proving limits, I can show you a problem where we're proving a limit, and that actually comes in handy that we can do that. So those are just some nice things to see, I think. Your book provides alternate proofs for these, but I thought I would just show these to you. Let's do some proofs involving sets. So we're still really only applying direct proof and proof by following sets. Direct proof and proof by contradiction, but we want to expand the variety of examples that we can use these in. Let's recall some things, and I'll try to define some things more specifically that we haven't defined yet. A, B, B sets, U, B, the universal set under consideration. If I say A intersect B, what does that describe? How would you define it? The set of all x in U such that
X is in
x is in A
And
x is in B at the same time. Okay. What about A union B?
X is in
X is in at least one, meaning x is in A or x is in B. And by the way, that's an inclusive or here, so it could be in both. Of course, sets don't repeat elements, so you'd only list it once in the union, but it can be in either or both. What about A minus B? How do we define that?
X is in U.
Sure, it's in the universal set such that
X is in A.
x is in A
And X is not in B.
and x is not in B. Right. By the way, the word but is equivalent to and for logical purposes. But just suggests that there's some sort of contrast that you want to make, but it's interpreted the same as and. So you could say x is in A, but x is not in B. What about A What is that?
Complement.
A complement, and what does that mean?
Everything not in
Set of all x in our universal set such that x is not in A. Right? Anything that is not in A is said to be in the complement of A. So all of these have little pictures that you can draw. I know we haven't really focused on the picture. So the intersection is what's in both, if that's A and B. The union would be what's in either of them, so you can shape both things. A minus B, like it's in A but not in B, so that would be this side here, that's your A and that's your B. And A complement would be if A's here hanging out, literally everybody is. Here's something I want to define. I probably said it in words, but I want to make sure I write it down. How do you prove that two sets are equal? Or let's talk about the subset. To say A is a subset of B means what? I want to get to a mathematical way to say this. Yeah?
B contains all the elements
B contains all the elements of A, sure. Is it possible to contain more elements?
It means given an x and A, that implies that x is also A.
Right. So it's true that B contains all the elements of A, but it could contain more. So using B is kind of going to be too big for a definition, I think. So the definition that we usually use is an implication. A subset of B means that it's an implication. If X is in A, then X is in B. Right? Everything in A is also in B. You have this, and this would be the picture, right? Here's your B, and here's your A. Your A is a part of B, perhaps equal to B itself, but it's clear that once you're inside A, you're also inside B. It's possible to be inside B, but not inside A, if you are talking about proper subsets. But that's what the, but that's what the being a subset means. And we're going to need to know that to prove all these things we're going to be proving. Okay, so now let me introduce the other one. To say A is equal to B, what are you saying? Yeah?
X is an element of A if and only if X is an element of B.
Right. X is an element of A if and only if X is an element of B. Right? In other words, that means X is in A implies that X is in B, and to break it down, X is in B implies that X is in A. But what is this our definition of?
Oh, so A is a subset of B.
Right, that's saying that A is a subset of B, and this is saying that B is a subset of A. In other words, two sets are equal when they're subsets of each other. I.e., A equals B if and only if A is a subset of B and B is a subset of A. So if you want to prove that two sets are equal, you have to prove these two things. Show that they are subsets of each other. Meaning they have precisely the same elements. If you know something is in A, it's automatically in B, and vice versa. If you know it's in B, it's automatically in A. It will be in both at precisely the same time, and it will be in neither at precisely the same time. So you do want to be able to tap out a multitude of ways to think about a certain concept. There's the pictorial way. You should be able to describe it in English somewhat, and you should also be able to write down some sort of precise mathematical definition that when you're proving, you know something that you can aim for to show something beyond the shadow of a doubt. Pictures in general, by the way, aren't proofs. You can't really prove something using a picture. You have to actually use language and logic. Okay. Let's prove some things now. This is something you would have noticed from your homework. But we're going to actually prove it. Or your homework indicated it, I should say, because you were asked to draw Venn diagrams here. At A, B, P sets. Show that A intersect B complement is equal to A complement union B complement. Right, so this is one of De Morgan's laws for sets. The complement of an intersection is the union of complements. Right? Now you did it in homework 1 where you actually drew these guys. Right? So you draw the pictures and you realize, oh, they look like the same. It turns out they're exactly the same. And now we know how to prove it. So let's actually do that. Prove it. What do we need to show?
Show the bifurcation.
We need to show
Left hand side is subset of the right hand side.
So we need to show that A intersect B is a subset of this guy. And we need to show that this guy is a subset of that guy. Okay. Okay, for one, how do we do this? How do you show that something is a subset?
Show it applies for all elements. So we start with arbitrary.
Show what implication? If I want to prove one, what do I have to show?
You show X is in A into that.
X is in this implies X is in that. So ultimately, to prove this, I need to prove an implication. Once we prove an implication, now we know we can direct proof, proof by contrapositive, whatever. Yeah.
Just because we haven't done proofs with sets yet, are you allowed to use Venn diagrams in proofs?
No, Venn diagrams in
Just
general
for your-
pictures
just
do
for
not
yourself.
constitute proofs. It can just give you an idea or an indication if something can work out, but you can't draw a picture and say that's the proof. That's not a thing. Right? Pictures don't have truth tables. You can't say that picture is true. Right? You can't say that. But it can indicate to you whether something is true or false, or it might actually give you ideas on how you want to prove or disprove something. So you might be tempted to say these are equal, or figure out what these are equal, and you can draw the picture and they'll look the same, but you have to actually prove it. Okay, so proving that it's a subset means I have to prove this implication. So for this, you need to show if X is an element of this guy, then X is an element of that guy. Okay, go. What do we do? What kind of proof do you want to do? You want to do direct? Okay, let's see how that works. Assume X is in that. Then what does it mean to be in a complement?
So X is in U minus the complement of that.
Yeah, but what does that mean to be in the complement of it?
It's not equal to, or it's not.
Then X is not in
A.
the intersection.
Yeah.
Okay. But that means what? How can you not be in the intersection?
So either on A or on B.
Strictly
You have to be strictly in A or strictly in B, which means at any given time you're not in one of them. Right? So this means that X is either not in A or X is either not in B. Why? Because the negation of that would be false, right?
Could we also say X is in A or X is in B exclusively?
Yeah, that's the same thing.
Let's say, okay.
Yeah, you can say X is in A but not in B, or X is in B but not in A. In other words, it's not in both. So it's also true to say it's either not here or it's not there, right? Because if it was in both places, it would be in the intersection, but you know it's not in the intersection. But this means what? To say that X is not in A is to say what?
A complement.
It's in the complement of A. it's in the complement of B. And to say that something is in one set or another set, what is that?
Union junction.
That's the union. By definition. So that's why those definitions are important. They give us something again to aim for, where we know we have the truth. So that was one direction. What about the second direction?
You have
Here what we do, we need to show. And again, this we need to show thing, you don't have to write it, but if you write it, make sure you actually write something like need to show. So I know you're not assuming something you have to prove, but you're just basically announcing this is what we're going to show at the end of the day. So you can do that, you don't have to include it, but you can, but make sure that when you include it, you don't confuse yourself and assume something that you're writing down is true and then use that. You want to avoid doing that, that's very interesting. So what we need to show here is that if x is in this guy, then x is in that guy. How do you want to do that? Directly? Indirectly?
Direct.
Assume x is in the union. Then
X is A complement or X is B complement.
X is in A complement or x is in B complement. Which means? What does it mean to be in A complement? X is not in A, or X is not in B, right? In other words, we have two cases here to deal with. So we end up with two cases. Here's a case 1, here's a case 2. But they're going to be pretty similar, so I'm just going to do without loss of generality. Without loss of generality, say X is not in A. Then
X.
it's definitely not in the intersection, right? Because to be in the intersection, you have to be in A as well as somewhere else. But that means that your X is in the complement of this guy. Right? And similarly, if you said, suppose it's not in B, then it cannot be in B intersect A, which means it's in the complement. We'll end up here either way. So that's that.
So I understand that, for example, if we wanted to try the contrapositive, we could say that assume X is in the subset A union B.
Alternatively. So you want to do the contrapositive?
Yeah, I just wanted to know how exactly you would write
So you
down.
would say that X is not in that. Right?
Well, I rewrote that as X is in the set of.
Yes, that would mean that X is in the set, right? If you're not in the complement, you must be in the set itself.
And I wanted to know for
And that would mean.
Well, I wanted to know for P, how would you write not P using part of the set? Like, how would you negate? Would it be?
Well, continue with this. What does this say? Like, I would start with the train of thought and just break it down into its most elementary parts, and then you can see how to use
Because
it.
the X is in A.
So this would mean that X is in A
And
X is in B. All right. So how are you going to use that to show that it's not in the union?
X is not, X is in A, X is not in A complement.
Right. It's definitely not in A complement, and it's definitely not in B complement.
So it can't be in
So it's-
or.
So it can't be in either or. So this means X is not in this or that either.
Thank you.
and then that gives you, it's not in the union.
So this would have been a better way to approach it.
I don't see much of a difference. They both seem fun to me. Either direct or contrapositive seems fun to me. Yeah.
Is that inclusive or exclusive? Because I'm trying to do the picture and I don't know, it just seems weird. Like,
What's inclusive?
from the beginning of your assumption, like after the assumption, then x is in A complement or x is in B complement.
I'm using the inclusive order.
Sorry?
It's inclusive order. Like if it's exclusive, we'll use dimension.
Okay, so
And we'll use like a negative sign to show that.
so would that mean that there's technically 3 cases then?
Where? You're talking about from this side?
Yes. You're saying that's the inclusive order, right? So,
Sure. Right, so it's possible that it's in both, but this wouldn't change.
okay.
Right, because both means it's in the intersection. Let's do another one. So that, you actually drew a picture for this in your homework, but it's nice to see that it's true. There's also the other one you can prove. Also, you know that if you take the complement of a union, it's actually the intersection of the complements. That's another De Morgan's law. You can do that as an exercise. It's probably actually in your homework, but I don't remember. But let's move on to another example. Just want to do a bunch of examples so you're kind of used to manipulating these things. Show A union B is not empty implies either A is not empty or B is not empty. Easier. You want to do a contrapositive? Okay. What would you assume?
A is empty and B is empty.
Right, that's the contrapositive.
Wait, is that just one case? Because then,
That would be everything. This is and, so they both have to happen literally at the same time. So it doesn't split into cases. They have to coincide.
okay.
This can have 3
Yeah.
cases. This won't, because it's and. It takes everyone all at once. So, and what does that mean?
It means both of them have no elements.
Yeah.
That
So
A
size of A is
union
0.
B is the empty set.
Right. So, A union B would be what? It's the set of all x's in U such that x is in
X is in
A or x is in B. But I know this is false. There is no x in A. There is no x in B. So what is the set of all x that is in one or the other? There are no x's that is in one or the other. It's an empty set. Which is not that. Almost so bad. Here's another example. Show if you have that A intersect B is the same as A, this will happen if and only if A is a subset of B. take the intersection of two sets and it's equal to just one of the sets, then it means that that set is a subset of the other one. Okay, let's break this down. What do we need to show here?
A intersect.
Which reminds me of another mistake on the homework. There was an if and only if problem, and a lot of people, I mean, like a handful of people, just proved one direction and didn't go the other way. If and only if, you have to go both ways. I think that was the one where it's like, oh, if 5x minus 11 is even, if and only if x is odd or something like that. A lot of people proved this way and they didn't go that way. But yeah, if and only if we need to show two things. So we need to show
A intersect.
that A intersect B equals A implies that A is a subset of B, and
A is a subset.
2, A is a subset of B implies that the intersection will be A. Now, let's actually break this down with our definition to see what we can do. What is this saying?
That's like a one sentence proof, right? Let x is in
No, I didn't start the proof yet. This is what I need to show. But what does this mean?
x is in A intersect B, which means that x is in A and B, and then you got it for free the second time.
I'm not doing the proof, I'm just asking the definition.
X is
Right, not everyone might see the proof right away, so I want to know, if you don't see what to do right away, how do you actually approach the problem? Right, you start by going through each piece that you see in the problem and writing down the definition, so that's what I want. What does this mean?
Means that some x is in A and B? Or do you mean the whole thing?
No, to say that A intersect B equals A, what am I saying?
So x is in A and x is in B, and x is in A, which is like redundant, but
all x's in A and B make up A.
B minus A is on this side?
Just go by the definition. Earlier over here, I wrote A equals B means
All elements.
A intersect B is a
means
subset.
A intersect B is a subset of A, and A is a subset of A intersect B. Okay. Now, what does that mean? What does it mean to say this is a subset of that?
X is in A intersects B.
X is in an element of A intersect B.
Which means x is in A and x is in B.
Implies that X is in A. And if X is in A, that would imply that X is in A intersect B. Right? Now, you won't always have to break things down this much, but in case you're lost, this is what you do, right? You start by just looking at the statements that you're given, break it down to the definition. If that still doesn't help you, break it down even further and understand that what you need to ultimately show is these implications hold, implies that that implication holds, right? And this one implies that X is in A means that X is in B, right? And now when we start to write that out, how to approach the problem starts to look a lot easier. So, right, and you can do that for this here. Just write down what all this means, just have all the information there, and you'll see how you can use it. So, let's do one. So, what do you want to do? Direct proof or direct proof?
Or indirect.
You want to do indirect? Okay, let's try that. Assume A is not a subset of B. Then, what would that mean?
X is in A, but X is not in B.
There exists some x that are in one but not the other.
That is in A but not in B.
But
Yeah.
the direction matters in who.
There's some.
Then there exists an X.
In A that is not in B.
Yeah.
Then there exists an x in A that is not in B.
Yeah.
But x not in B, that means
A minus B.
we don't need to go there. Ultimately, what we want to say something about is A intersection, right?
It's not in the intersection.
It can be in the intersection. Right? Because it's in A but it's not in B, therefore it's not in both.
Oh, okay, so it's exclusively in.
And that also implies that A intersect B is of course not A, because I have something in A that's not in there. And yes, you could do a direct proof and I don't think it would be much longer, it would probably be quicker this way. So yeah, that proves this, right? We proved that by the contrapositive. Let's do 2, which, yeah. So what do we want to do here? We want to do a direct proof?
Yeah.
Assume A is a subset of B, right? I'm assuming the first part of the implication. Then, what does that mean?
X is in A, X is in B.
X is in A implies X is in B, right? So if there is an X in A, then it will also be in B.
Can we use and?
No. So I'm assuming this, it means this. What I want to show is that this is equal to that.
Then does that mean X is in A intersects B?
Right. So if X is in A, then X is in B, which means that X is in both. And this shows that A is a subset of the intersection. Right? Because I assumed X was in A, I got that X is in the intersection, the implication goes this way, I showed this subset relationship. Now if your X is in A and B, then clearly X must be in A. So A and B is a subset of A. Which, that by the way is always true. And so this means ultimately that A intersect B is equal to A. Right, because I showed the 2 subset relationships. And that by definition is what equality means. I wanted to get to contradiction today, but we probably won't get to it. Let's just have some more fun, some more sets. Let's do Cartesian Products.
I don't really understand like the last one. So you said X is part of A.
How about here? Or here?
Yeah, 2.
2, okay.
So you say X
So I'm
is...
assuming this is true, I want to show that that is true. So I assume this, that is this by definition.
Okay.
Right. So now, what I want to show is this first. What this means is that X is in this implies X is in that. So I assume X is in A. Then by this assumption, X is in B.
Okay, so it's in the intersect.
Right. I can say this because of this here.
How do you make the jump from X being in the intersect to A being a subset of A? Oh wait, that's the part of it. Okay.
Yeah, because I can make that jump because I said this implies that. So I can say this.
Okay. Yeah.
Right. And this gives me that, which allows me to say that, gives me that.
Okay.
Right. So this assumption tells me that once it's in A, it's in B. To prove this, I have to assume it's here and show it's there. So I assumed it's there, but I get that's in B because of this assumption, and so it's in both. And so that proves that relationship. If I assume it's in both, then clearly it's in one of them. This is always true. I don't even need this assumption here. This is always true. Right? The intersection between a set and something else is always a subset of that set. Groups involving, and this is again going to come in handy when we're in chapter 8. Chapter 8 and 10 are very important. Well, all the chapters are kind of pretty important. Cartesian Products of sets. You guys remember what Cartesian Products of sets is? Recall. Talk about the product of sets. A cross B is the Cartesian product of A and B, and that is defined to be the set of
A and B.
What are the elements look like?
So ordered pairs of
They're ordered pairs,
Yeah.
right? So it's the set of coordinates such that the first coordinate is in A, right? So it's putting them in a certain order, and the second coordinate is in B. So sets by themselves don't impose any order on the things that you're doing. So if you want to impose an order, you use a Cartesian product, where you can actually order things. They come in a certain order. You can use repeats to get repeats if you want, and so on and so forth. So this is called the Cartesian product of A and B. And of course it can extend, right? So this can extend to any set you want, any number of sets you want. So that's just a set of triples. Such that the A is in A, the B is in B, the C is in C, etc. Right? This can go on for all. Right? You can cross a set with itself in general, and then you'll call it just that square, right? And that's where R2 comes from and R3 comes from. So we're just building up a set of coordinates, we're ordering the elements. So just remember that. Let's actually prove some stuff. Proof. If A cross C is a subset of B cross C, if and only if A is a subset of B. We need to show two things. One, if A cross C is a subset of B cross C, then it means that A must be a subset of B. And two, if A is a subset of B, then it means that A cross C is a subset of B cross C. How do you do one?
We could use it direct.
Sure. Which means you're going to assume that A cross C is a subset of B cross C, and we need to show that A is a subset of B, right? Which means once you say that, now ultimately your goal is you need to show that X is in A implies X is in B, right? You ultimately want to show this is true based on this assumption. Okay, so what does that mean?
What
an arbitrary ordered pair be given in A cross C, so X comma Y is in as an element.
Okay, so that means that x comma y such that x is in A, y is in C is a subset of x. Well, x is in B, y is in C. Maybe not. Because I don't want you guys to say anything too sloppy. What would you do here?
Can we keep the y and use z, or should we use different variables for this at c?
Use m and n. Right. These two sets are subsets of each other. What can you say now?
Wait, Professor, I have a question. Before that edit you just did, could you write that though, since you are given that it's a subset?
Yeah,
You could.
we're assuming this, and this is literally saying that. I'm just writing it out so that you can see the kind of object.
I know, but I'm saying the revision that you made, you changed the letters, right? But could you have kept it the same? Because
The
you,
variables that we're using.
Well, technically they won't be the same all the time, so no, I won't keep it.
under that assumption.
No. Yeah, what does that mean? Then,
Intersect.
this means that if there's a coordinate in the first one, then that coordinate must be in the second one. Right? That's the definition of what it means to be a subset. So if we're in here, it means this is in there, but this is in there means what? But then xy is an element of B cross C means that x is in B and y is in C. And that gives us A as a subset of B. Why does that give us A as a subset of B? Because assuming this means I'm assuming x is in A and y is in C. Right, so I'm saying if this is true, then that is true. But this means that. So ultimately I have x is in A, and that implies that x is in B. So that means A is a subset of B. Sets can be a bit tricky. Sometimes you have to go home and you have to sit down and you have to read them back slowly. You draw a couple Venn diagrams to the side. Eventually you'll get used to it. Assume now, I want to show this one. So let's do a direct proof. Assume A is a subset of B. Then x is in A implies that x is in B. So if xy is in A cross C for y and C, then it also means that xy must be an element of B cross C. Which means that A cross C is a subset of B cross C. So assume they're subsets, that means this by definition. But that means this coordinate would be in A, I'm assuming X is in A, but that would also mean that that coordinate is in B cross C, because that same coordinate is in both of these guys. Yeah.
Sorry, I'm a little slow. P implies Q.
Yes.
What is the state to assume? P or Q? And when it comes to P implies Q, what is the state to assume when you're proving P or Q?
Oh, to prove P implies Q? To prove P implies Q? I think you were just absent for those classes because you registered late.
Which one is safe?
You have direct proof. So what you can do is you can assume P and then show Q ultimately. You have what's called proof by contrapositive, which means you can assume not Q and then show not Q. We also have, well, this is what we're going to do next time because we don't have time to do today, contradiction, where you would assume P and not Q and then show C. This is the contradiction. But so far, these are the only two we have. So if you want to prove an implication, you're either going to assume the thing that's in front or assume the negation of the thing that's in the back. Yes?
Is it necessary to show the case in which y is not in Z?
If y is not in C, it's not in the Cartesian product. To be in this set means that element is in C. And we don't really care about elements that are not there because we're only proving things that are here. There are no complements here. So whoever's in the complement can do what they want. I don't care. I'm talking about things that are in the complement. So I only care about the y's that are in C anyway. Yeah.
Oh, that was me, sorry.
Oh. Show this. A cross B complement is actually not the same as A complement cross B complement. Ideas.
Write the definition of A cross B.
Huh?
Write the definition of A cross B and the definition of.
Okay, so what's that definition? Here. This is just all the set of things that looks like x comma y such that your x is in A and y is in B, and we're taking the complement of that. So what does that mean?
X is 9A.
The pairs of x, y. Or
So it's all pairs f of x, y, which are like the universal set cross the universal set, such that x is not in A or your y is not in B. Okay? What does that mean?
You mean the X is
That is. So we're saying that if such a coordinate is here,
X is A complement?
if x is not in A or y is not in B, then here
X is A complement.
x is in A complement.
B complement.
Yep, does that show what you want to show? They're actually not equal, like we know this.
Professor, where did the or come from?
The negation.
Oh, that should be in.
Isn't it?
We said it's in the complement, so I want all coordinates such that they are.
X is in A and Y.
Wait, sorry, is that for the first one? The left-hand side?
We were just writing down the left hand side.
Oh, okay. Let me just try.
So A cross B complement, these are all the things in A cross B. And we took the negation of that. So either the first coordinate is not in A or the second coordinate is not in B. That's right.
Thank you.
Then can we just write it as the set of, oh, well, wouldn't just not A cross, not B be the set? Oh, it's like the same except the or is an and, so then you know they're not equal. On the
Yeah, but that's where you're going to want, making that observation is where the proof is going to come from. I'm saying they're not equal. The thing is, or can include and. You basically want to show why the inclusiveness of this messes that up.
You could say not every element.
Yeah, but how do you show that?
So
Yeah.
definition of equal, we said, was one is a subset of the other,
Yeah.
and then the
Okay.
reverse. So pretty much what you want to show is that, and the way you could do it is, I lost my train of thought, sorry, but yeah.
So you want to show that either this is not a subset of that or this is not a subset of that.
Yeah.
That's what you want to show. So how do you go about doing it?
Can you first write out the right hand side, just to get a visual comparison to the
Okay, so what would the right hand side look like?
It's just the same thing.
set of
Set of coordinates x, y, such that x is not in A and y is not in B.
This is not in A and Y is not in B. Which would be?
X is 9A and Y is 9B.
X is in A complement and y is in B complement.
X is in A complement and Y is in B complement. Sure.
Then we want to show that x being
So let's actually use a picture to help us out here, right? Let's say that's my A, that's my B. Where is this claim, what were complements? Where is this claiming that we live?
it's everything but the intersection.
Right, I could be over here, or I can be in here, or I can be here. Right?
Sorry.
Where's this picture saying that we live?
Uh,
Because that's my A complement, that's my B complement. This says what?
It's in the intersection.
I'm right here, which I can't be here, I can't be here. So that's kind of telling you the guys that we're going to want to expose to show that they're not equal. Because if I can find a guy that's here, it will work here, but it won't work there.
Wait, that
Wait,
picture
wait,
is
wait.
actually the outside, right?
it's the outside of both circles.
I'm
The
doing
circles
the,
are-
I'm doing, I did a
Oh, this.
I put a bar over things. It's A bar.
Oh, I see, okay. It's like an inverted world or something.
Yeah. Bizarre world. Yeah. Right? So guys over here live here. Guys over here can live in any three of these. So I claim that the guys over here can potentially be bigger. You can have a larger set of things over here than you have over there.
So would you show that?
So what you can do is you can kind of make a proof where, and this we'll get into more next time as well, you can kind of make a proof where you isolate one of these guys here. Like pick a coordinate that's such that it's formed by the guy over here, and show that such a coordinate would not exist over there. Another way to do that, which this is getting into chapter 5, is the idea of a counterexample. Right? Now looking at those pictures, could you maybe come up with a specific example that shows that I can tell you about two sets A and B, where if we form these guys, they're not the same?
Yes.
Sure. Well, that's in theory, that's what we're getting. Give me an example then. Try to construct it. There's a way to prove this in general, but I want to also see your example muscles put to work. And this is going to go into chapter 5, where we're going to talk about disproving general claims or proving specific claims, existence, and proof by contradiction. So give me a U, an A, and a B.
How specific do you want these examples?
Specific as you want.
Can you be?
It might be easier to just use some small sets, yeah?
Can you be?
Let's say U is 1 through 10.
Huh?
U is 1 through 10.
1 through 10?
Yeah.
I probably don't.
It's not.
Remember what? Okay, let's do 1 through 10. And what would A be?
So let's say A is 2 and 3.
2 and 3, okay.
And then let's say B is 3 and 7.
3 and 7. So you're just throwing some random examples out there.
Yeah.
How many things would be in A cross B?
4 and 4. Yeah. Just a regular A cross B without the complement.
I think having that 10 is going to be a lot to count. Well, we have someone who did combinatorics in here. So what would A cross B look like?
2, 3, 2, 7.
No, because here's, that example is going to get really crazy. Because I'm ultimately going to want to construct this, right? And then I'm going to want to construct this. Right? Now that is going to have a lot of elements, right? Because there are going to be 8 possibilities for this
You want
one.
to make it through 5?
And 8 possibilities for that one. Probably don't want to do that. Let's actually cut this down a little bit. Let's say we did, and this is how you want to start building examples. Don't go 0 to 100. Just start with a few, like 1 or 2 things, and maybe let's do one thing here. Okay. Okay. Given that, what is my A complement and my B complement?
A complement would be 1.
My A complement would just have 1 in it. My B complement would have 2 and 3.
This is
And so if I were to take A complement cross B complement, what would that look like?
Instead of 1,
1,
2,
1, 2,
1, 3.
and 1, 3. Okay. And what if I took
A cross B.
A cross B?
0.
You get 2, 1,
2, 1, 2,
maybe 1.
the regular one.
Let's look at A cross B.
You get 2, 1,
3.
A cross B. You get 2, 1,
and then 3, 1.
and then 3, 1.
Order doesn't matter, right?
Order matters,
Oh.
right? Now, what does U cross U look like?
1, 1, 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 2, 3, 3.
It's like 1, 1,
1,
1, 2,
1, 3,
1, 3,
2, 1,
2, 1,
2, 2,
2, 2, 2, 3. When you'll be able to see it after this.
then 3, 1, 3, 2.
3, 1, 3, 2, 3, 3. So what can I say the complement of this is? Or how many things would actually be in there? You can even look at that.
7.
7?
How many things would be in here?
7,
7. How many things are in there?
2.
2.
They're definitely not the same. I have a different number of elements in each, right? And you could actually just write out what that is. Right? So this is actually something we'll actually do more of next time. There's actually a general proof for this. You guys can actually try it at home and we can see tomorrow if one of you can suggest to me how we can actually prove that directly. But this is actually a bona fide way to prove that this is not equal. Give me an example. I can tell you examples of sets A's and B's where they don't work out. Constructing examples, simpler is better. Don't just go all the way, especially when you have things where they can kind of alternate like this. You don't want to spend too much time. You don't want to have to write out like 64 coordinates. That's going to take too long. But we'll stop there. We'll pick up next time. We'll do one more example of this, and maybe I'll have one of you describe to me how you'd actually prove this in general if you don't want to do an example. And then we'll talk about proof by contradiction and existence of an use. If you came in late, make sure that I mark you here and you pick up your homework. I'll see you guys tomorrow. So we're not done with chapter 4, so go over what we do here very slowly, and the homework is going to be due after tomorrow.